Okay, in this video we will prove the limit that the ratio of sine of theta of the angle theta over theta as theta goes to 0 is equal to 1, and as a matter of fact the limit of theta over sine of theta as theta goes to 0 is also equal to 1 if you just follow the properties of limits. Okay, in order to solve this in order to prove this limit, we will need some knowledge of trigonometry. And if you have a right angle triangle with angle theta here, let's call the hypotenuse, which the hypotenuse is the side opposite of the right angle, that's why it's called right angle triangle, let's call that hypotenuse C. The side opposite of theta, let's call it B, and the side adjacent to theta, let's call it A. Okay, so these trigonometric functions, sine of theta, cosine of theta, and tangent of theta, are nothing else but the ratios between the sides in this right angle triangle. Sine of theta is the length of the opposite side divided by the hypotenuse B over C. Cosine of theta is the length of the adjacent side divided by the hypotenuse. And tangent of theta is the ratio between the opposite side B over the adjacent side A. Okay. Moreover, we will need to know the area of a sector of a circle. So recall that if you have a circle with radius r, okay, the area of this circle is going to be equal to pi r squared. Okay. Now I want to find the area of this sector here, only this part here. Okay. Still has the same radius r, and this is the angle, let's call it theta. Okay, so the area of this sector is going to be equal to how much? Well, pi r squared, the area of the whole circle, times theta over 360 degrees, or that's 2 pi, right? So I'm taking only this angle with respect to the whole circle times the area of the whole circle. And then if you simplify this, you get the area of a sector. 1/2 theta, which is the center angle, times r squared. Okay, so this is what we need in order to prove this limit, plus the squeeze theorem that we have covered that one in class. At the end we will use the squeeze theorem. Okay, so let us start by sketching a unit circle. Okay, and unit circle is a circle with radius 1. Okay, and let's have a sector here with central angle theta, right? The radius is equal to 1. Now I'm going to take only this part, only this sector, and I'm going to zoom in a little bit. Okay, so what did we say? This side here is 1, it's the radius, right, this side, and this one also is the radius, 1, and this is here the angle theta. Now the area, let's call this point O, and this point A, and this point B. So from this formula here, the area of this sector OAB is equal to 1/2 times theta times r squared, but because r is 1, I have 1/2 times theta, or theta over 2. Now I will create two triangles. The first one, by just dropping a normal line to the line OA from the vertex B. Okay, and then I obtain this right angle triangle. Okay, let's call this side here B, and let's call this point here C. What is going to be the area of the triangle OCB? Okay, well, that's equal to 1/2 times B times A, where this side here, be careful, this whole length is 1, so this length here I'll call it A. Okay, so the area of this triangle here, OCB, is just 1/2 B times A, or 1/2 AB. And then I will create another triangle. Okay, again, it's a right angle triangle. Okay, so the area of the triangle OA, and let's call this D, this point OAD, is going to be 1/2. Now look at this. This side here, which I can call N or M, okay? M times, so M times this side, but this side is 1. So the area of the triangle OAD is just 1/2 times M. Now, because I said that we're going to use the squeeze theorem, we have to come up with some kind of inequality, okay? This limit can be proved in many different ways. Somebody is comparing the length of B times this length right here times this length, the length of M. But I think it's more visible to conclude that the area of the triangle OCB, so the area of OCB is less than the area of the sector, right? It's less than this area. So that's less than the area of the sector OAB, and both of them are less than the area of this big triangle OAD, right? This one is the biggest, has the biggest area right here. Okay, so that's OAD, the area of OAD. And because we have found expressions for each one of them, okay, let's write them down. So this is OCB, the area of OCB is 1/2 A, this side A, then this side B, which is less than 1/2 times theta, which is less than the area of OAD, which is 1/2 times M. Now we want to bring trigonometry into this whole calculation. So let us use trigonometry in order to find expressions, in order to find the values of A, B, and M with respect to the central angle theta. Okay, so I'm going to sketch this triangle just one more time to be a little bit more clear. Okay, so I had O, A, B. This here is the length B. This is the length A. This side is 1. Okay, and then we created one more triangle, and this side here was M. Okay, so first of all, how much is A and B with respect to the angle theta. Well, what did we say? Right, this is here. It's 1 because it's the radius of a unit circle, right? Okay, so how much is going to be sine of theta is equal, sine of theta is opposite over hypotenuse, that's b over 1, which means it's only b. So b is equal to sine of theta. Similarly, cosine of theta is the adjacent over the hypotenuse, so that's a over 1, or simply a. So a is cosine of theta and b is sine of theta in a unit circle. Okay, and finally m, the value of m, tangent of theta is equal to the opposite m over the adjacent, and the adjacent is 1, so that's equal to m. So on the previous page we established this inequality: 1/2 AB is less than 1/2 theta is less than 1/2 m. And now I have values for a, b, and m with respect to theta, so let's substitute those. So 1/2 a is cosine theta, b is sine theta, less than 1/2 times theta less than 1/2 m is equal to tangent of theta. Okay, so what can we do now? Let us multiply this whole inequality by 2 over sine of theta. Okay, and this is going to be a positive number because theta is between 0 and 90 degrees. Okay, if you multiply inequality by a positive number, these inequalities are not going to change. So you guys do this by yourself. What are we going to be left with is cosine theta less than theta over sine theta less than tangent of theta over sine of theta. Well, I don't know if it was mentioned before, but the definition of tangent of theta with respect to sine and cosine is sine of theta over cosine of theta. That means that tangent of theta over sine of theta, an expression that we have to work with, is equal to sine of theta over cosine of theta, that's the definition of tangent, over sine of theta, cancel sine and sine, and you're left with 1 over cosine of theta. So, with this identity, we can rewrite this inequality as cosine of theta less than theta over sine of theta less than 1 over cosine of theta. Okay, and at this point we can stop here with simplifying this expression, and we just call this function here f of theta, we call this function here g of theta, and we call this function here h of theta. So the question is, how much is the limit of g of theta as theta goes to 0? Well, having this inequality here, what can I do? I can evaluate limit of f of theta, which is the limit of cosine of theta as theta goes to 0. Just by direct substitution, this is cosine of 0, and cosine of 0 is 1. Limit of h of theta as theta goes to 0 is equal to the limit as theta goes to 0 of 1 over cosine of theta. By direct substitution is 1 over cosine of 0. Cosine of 0 is 1. So again, I have 1. So look at this. On one hand, this inequality is satisfied. On the other hand, this limit here approaches to 1 as theta shrinks to 0, and this function here approaches to 1 as theta goes to 0, this means that by the squeeze theorem, limit of g of theta as theta goes to 0, or more importantly, limit of theta over sine of theta as theta goes to 0 is equal to 1. Okay. But how I will use this in order to prove our limit of sine of theta over theta as theta goes to 0 that is eventually equal to 1? Well, I can rewrite this as 1 over the reciprocal of this, which is theta over sine of theta. Okay, make sure that you understand what's going on here. Okay, we just proved that this limit goes to 1. So 1 over 1, because the denominator approaches to 1, 1 over 1 is equal to 1. And there you go, sine of theta over theta as theta goes to 0 approaches to 1. From here, you can easily prove that limit of cosine of theta minus 1 over theta as theta goes to 0 is equal to 0. How to do that? Use direct substitution. Cosine of 0 is 1. 1 minus 1 is 0 over 0. I have this limit here that I know of at this point. So I'm going to multiply the numerator by cosine of theta plus 1 over cosine of theta plus 1. Where am I going with this? Well, by difference of squares, the numerator becomes cosine squared theta minus 1 squared divided by theta cosine of theta plus 1. Now, the most important, the most basic trigonometric identity is that 1 is equal to cosine squared theta plus sine squared theta. And from here, 1 minus cosine squared theta is equal to sine squared theta, right? If I just bring cosine squared on the other side of the equation. That means you can factor -1 here and get 1 minus cosine squared theta over theta times cosine theta plus 1, which gives you the limit of negative sine squared theta over theta cosine of theta plus 1. Make sure that you understand where I write the exponent of sine squared theta. So just when you see sine squared theta, this means sine of theta times sine of theta. And here I have limit of negative sine theta times sine theta over theta times cosine of theta plus 1 as theta goes to 0. And now this limit, you already know it. Sine of theta over theta as theta goes to 0 approaches to 1. And this goes to limit of negative sine of theta over cosine of theta plus 1 as theta goes to 0. Use direct substitution and you get negative sine of 0 over cosine of 0 plus 1. Now you should know that sine of 0 is 0, cosine of 0 is 1, 0 divided by 2 is 0. So basically we have just proved this limit, the limit of cosine of theta minus 1 over theta as theta goes to 0 is equal to 0.